Hello, I brought another example for conditional probability. Okay, sorry. So in this example, we are going to think about the relationship between tuition and salary. So let's simplify the question. We observe data like college graduates, and we observe their salary, and also we observe their tuition, how much tuition they paid. So we ask a question. If you graduate from a high tuition school, then do you make high salary or not? So simply, we are going to just, it's on and off. T stands for high tuition school. S stands for high salary. Then automatically T complement means uh, graduated from a school that does not have a high tuition. And S complement means earns a salary that is not high. The definition of high tuition and high salary, it's up to you. It depends on like price level, inflation, and things like that. Anyhow, so simplify. It's a yes or no, high or low, high tuition, high salary. And then we would like to answer this question: does high tuition pays you off, makes you more likely to earn high salary? And then again, which probabilities do you have to calculate to compare? This is the most important question you have to learn from statistics. Okay? Uh, I mean, in this chapter, not in general statistics, at least in this chapter, up to here, this type of question is the most important. Okay, think about it and then resume. Now I'll turn the page. So I'll explain this. So then now again, the comparison is those who graduated from high tuition versus those who graduated from a low tuition school, right? So if you graduated from high tuition school, how likely you are to make a high salary, right? And in this sentence, if you graduate from a high tuition, that already means the condition is high tuition school, right? So T versus you are going to compare if you graduate from a low tuition school, how much would you make? So condition is T complement, excuse me. T complement low tuition versus high tuition, but we are looking at the same salary, same event, looking at the salary, right? So basically, B is the right comparison. You have to fix the main event, but you flip the conditioning event. That's what you have to do to answer this question. Okay? Okay, so I this is like if you get it, then from here it's mechanical, right? We like suppose that you have this table. This probability table is again made up numbers. It's not real. But suppose that like you get these numbers and calculate these two probabilities and make your own conclusion. Make your own comparison and which is correct, which inequality is correct. Find out by yourself, calculating the conditional probabilities. You may copy those numbers to Excel or you may use a calculator. It may be a little annoying algebraically, but still simple. If you can write down the numbers, the calculator part should be simple. Okay, stop the video here if you have not finished. Let me tell you, the answer is this. So if you condition on T, then you use the first row only. So denominator is here, numerator is the first column entry, right? And if you condition on T complement, you have to use the second row, which is in the denominator, and numerator is this guy, high salary. Okay, so that means if you do the math, you get the same probability. This implies that no matter where you graduate, the chance of high salary is the same. According to this hypothetical data, right? I'm not sure if it's true in reality, but at least in this example, in this numerical example, you get the same probability. Okay, now we will think about this interesting special case. Now then, it is interesting to see another probability, that is unconditional probability, right? Out of all the types, four types, what is the probability of high salary regardless of your tuition level, right? High salary, this event includes these two outcomes, right? Out of four outcomes, we are interested in the first column, two outcomes. Then, anyhow, we know the sum of four probabilities must be 100% always. So denominator is automatically 100. So we don't care about that. And numerator is these two. So that is also 25, right? This is a very interesting but intuitive. I said if you graduate from high tuition school, probability of high salary is 25. Even if you don't, still it is 25. Then unconditionally it will be also 25. There will be no other possibility, right? So probability of high salary is, in this example, always 25, no matter how you condition on. Unconditionally 25, or conditioning on high tuition or low tuition, always 25. Does not change. So this is a very interesting and specific special relationship which is really important in the future analysis. And so we call them statistically independent. This is very important, right? So probability of A unconditionally, or conditioning on B, or conditioning on not B are the same. Then A and B are independent. And if this is true, mathematically, you may flip the effect of like condition and main event. So if this is true, you can also think about probability of B. Probability of B will independent of conditioning on A or not, right? So this is a special case where one event, probability of an event is independent of conditioning on the other, right? No matter what happened to B, A's probability is the same. Let me give you example why it is important, because like you may interpret that B is not effective to change A, does not affect A at all, right? Or information about B does not help predict A, right? Because B does not affect A, so you don't need to observe B when you estimate probability of A, right? Or like in terms of comparison, there is no difference. Comparison, they are the same. That's exactly what we do. So especially the second interpretation is very interesting, and it simplifies our analysis a lot in the future, because like when you know that this information does not predict A, then you don't need to observe, you don't need to worry about B at all. In your analysis, you can just delete this. So you can simplify your analysis, right? For example, like in a more economic context, like today's stock return, if today's stock return is independent of tomorrow's stock return, then when you predict tomorrow's stock, you don't need to observe what's going on now, because they are independent. It does not help. Or if you believe that Chinese GDP growth, for example, GDP growth is independent of the United States GDP growth, then you don't need to look at Chinese GDP when you are worried about the United States GDP. Of course, these are not true. These independence will not hold in reality, but if you believe they are independent, then your analysis will be much easier, right? If you can rule out some information in your analysis if you assume that they are independent. Okay, so anyhow, in your statistical analysis, it is impossible to all information in your analysis. You have to have a boundary and assume that anything you don't observe is actually independent. Because so, as a result, they don't affect your forecast, right? Something like that. So statistical independence is very useful in your analysis, and we are going to use them again in the future soon. And then also the independence implies a very interesting result to the multiplication rule. So this is the general multiplication rule. The probability that A and B happen at the same time can be understood as the probability that B happened first, and then given that condition, A happened, right? So I explained that as simultaneous or sequential interpretation. Does not matter. Anyhow, this is true in general. This rule is derived from the definition of conditional probability, just moving this probability from the denominator to the other side. But what is interesting here is if this in the middle, the conditional probability can be simplified to a unconditional probability, then this is really simple, right? So under a special case, under a special condition that the conditional probability equals unconditional probability, then the intersection's probability is multiplication of two simple probabilities. It's special multiplication rule, right? So by the way, to understand this, you can think about special addition rule in chapter 1. Near the end of chapter 1, I introduced special addition rule, where that means probability of union is sum of two simple probabilities under a very special condition. The special condition was mutual exclusiveness, right? This was the special condition required for addition rule. But now, for multiplication rule, union is replaced by intersection, addition is replaced by multiplication, and mutual exclusiveness is replaced by independence, statistical independence, right? However, statistical independence has nothing to do with mutual exclusiveness. If two events are independent, still they may be mutually exclusive, or vice versa. So there is no relationship between these two, but the structure of two different formulas are pretty similar, parallel, right? So anyhow, you are going to see this simplification later a lot, right? Because again, it is simple. It simplifies. In some sense, if they are independent, marginal probability about A, marginal probability about B can give you joint probability, right? If they are independent. That's another interpretation of this, right? So independence is really, really strong and useful case. Okay, then what's more complicated is in the first chapter we learned mutual exclusiveness. How do we check that? That's simple. Calculate the probability of intersection. If it is 0, then mutually exclusive, otherwise not. But if you want to check if two events are statistically independent, it's not as easy, right? So I will discuss that here. You have data and you want to see two events are statistically independent or not. Like in our example, you'd like to test if tuition is independent of salary, right? That's curious. That's an interesting question. We are curious about that. And how do we check that from data? There are two different ways, right? So we learned if two are statistically independent, both properties must be satisfied. If A and B are statistically independent, first, you know the probability of A is the same regardless of condition. B, the probability of intersection should be multiplication of simple probabilities. So these two are results following statistical independence. So when you are curious if two events are statistically independent, you can test if this hold or this hold, right? Mathematically, you just need to show one equality. There are three equalities, right? Here. If you can show one of them, that's it. If one of them is true, then two events are statistically independent. Okay, that is how we verify statistical independence. Okay, so now back to the tuition and salary example, we are going to test their independence using the first method. First method is based on this property, right? This should be true if they are independent, right? If they fail, if this equality fails, that means they are not independent, okay? That's what you're going to do. But as I said, you don't need to show all three at the same time. If you can show that any two of them are the same, then automatically the other follows, right? So you just need to show one of these two. What should I show? It's up to you. Just find two probabilities that is easiest to calculate, right? If you, it's up to you. Depending on what kind of information you have, one probability may be more convenient to calculate. Then use that, okay? But what you have to be careful is here A is fixed, but condition is changing. Remember, the interpretation was the probability of A does not change no matter what the condition is. So even if you change the condition, probability should be the same. That's what you are showing here. So if you try this, it's wrong. This is nothing. It doesn't mean anything. Okay. Back to our example. You may think about one of these six using T as condition or using S as condition, and given like choosing one of them, and then choose any pair, any equality pair, right? So whatever you like among six, but you have to change the condition, fixing the main event. It's up to you. In this case, like okay, as you see, fix the main event, but change the condition. Like as an example, I'm going to test the unconditional probability of T with probability of T given S. When I change the condition to S, I will check if the probability of T changes. So unconditional probability of T is 45%. Just out of 4 types, we are interested in these 2 types. So sum them, then you get 45%. But when you condition on S, you delete the second column and only use the first column. Denominator is sum of these 2. Numerator is T, one entry. That is also 45. So they are equal. That means if you can show this equality, so here I just showed the 4th equality. If you can show one, the other 5 equalities are automatic. They are true too. The other 5 will hold automatically if you can show one. Okay, this was the first method. And the second method is based on the special multiplication rule, right? If they are independent, this will be true. And if this is wrong, they are not independent, right? So we are going to calculate this, and we are going to calculate this, and then multiply them, and see if they are the same or not, right? In our example again, left-hand side is S intersection T, which is just one outcome, 11.25, and then you calculate unconditional probability of S, which is these 2 outcomes, sum them to get 25%, and the other simple probability, marginal probability, T, is these 2 outcomes, which is 45%. So you calculated 3 probabilities. then what you have to do is multiply two simple probabilities. And you do it this way. As I said earlier, be careful of percentage unit. Percentage unit may confuse you, so I recommend this way. Then in the end, you get 11.25, which happens to be the same as intersection, right? So the special multiplication rule is true, so they are independent. Okay. Okay, so then back here, as I said, first to test statistical independence, to verify two variables are statistically independent, you have to verify one of these two, right? So if you decide to verify the first one, you have 6 options, but just verify one of them. That's enough. Okay. If you decide to verify the second equation, there is no choice but just calculate 3 and compare that. That's what we can do. And in this example, like, it doesn't matter what you choose, the conclusion should be the same. So you may try multiple different methods and compare if they are the same decision, same results. Otherwise, there might be some mistakes. And in this example, I would do the second method because we have this table, and I personally I think this algebra is easier, right? It's easy to calculate on conditional probability. Then take that method, right? That's what I propose, what I recommend. But it doesn't matter what you use, and depending on the form of the information, one may be better than the other. If you already have conditional probability, that will be better. Okay. Okay. Thank you for watching. So far, in 3 videos, we defined conditional probability. We learned how to calculate them, and we learned independence and how we learned how to verify independence. So up to here, basically what we learned is like this. We have joint probability distribution, and based on the joint probability, we studied conditional probability, how to calculate them, what's the properties. But in the next video, we will go the other way. Our information is given in the form of conditional probability, which is common in economics. Many information is given as conditional probability, but from the conditional probability, we would like to calculate unconditional probability. Then what should we do? That is a different and very interesting, useful question that I'm going to answer next time in the next video. Okay, thank you for watching. See you in the next video.